Hello, you're back for more. I know that last section was kind of a doozy. It was a long video, lots of problems, very complicated. But I think that's one of the harder parts of this class is that section. So if you can get through that, I think you're doing pretty good. And the more of those problems you do on your own, the easier they'll get. So don't worry. And this section is applications of systems of equations. So what we're going to have to do is we're going to read the problem, it's some kind of word problem, and we're going to have to come up with the system of equations on our own based on what they give us. And if that sounds scary, don't worry. The good news is, once you set up the system, it's usually really nice. You're going to solve it with whichever you like, substitution or elimination. You have the freedom to choose either one you want. But usually you're going to be surprised by how easy it is once you set it up. So we've seen a lot of kind of application sections so far. But what I would do is probably, as it says here, there's not really a lot of theory behind this section, just more jump into these problems. But what you want to keep in mind is you're setting up a system of equations. So when you read this problem, it should be giving you enough information to set up two equations, some equation with an x plus y equals something, another equation with x and y equals something. They may not look exactly like that, but they'll give you enough information for two equations, both of the equations having an x and a y. Or you can use whatever variables you want. It doesn't have to be x or y. Okay, so you're gonna, okay. But what you want to do for sure, if you're kind of stuck, like it says here in the directions, assign two variables, say x or y or whatever variables, to the quantities that you're asked to find. So it's a good idea to read the problem, kind of make sure all the words make sense. Look for what are they wanting me to find, and let your variables be equal to those things. Okay, then let's try to look at example 1 and see if we can't figure out what to let our variables equal. So in example 1 it says, in 2010, solar and wind energy generation totaled 1,033 trillion BTUs, which are British thermal units. Wind generated 52 trillion more than 8 times that generated by solar energy. Alright, that's going to be a complicated one, huh? But I'm just scanning this to make sure it makes sense, and then in the end I'm trying to see what are they asking me to find, and I'll maybe make my variables be equal to those things. So they're asking how much was generated by each source. I guess in the end what they want is, they want some variable equal to, I guess, the number of BTUs that one of the sources made. BTUs for solar, maybe? That's how much solar was generating. And then let something be the number of BTUs for the other type, which was wind. And this is where it's up to you. If you're a stickler for x and y, you could let solar be x and wind be y. But I think in the end, what if you do that? You let x equal solar, the number of BTUs that solar generated, and you let y be the number of BTUs for that wind generated. And if you solve in the end and you find x, you're going to forget what x was. Which one was that, solar or wind? But it's up to you. I do like to use, for example, S for solar, W for wind. To me, that just makes it easier. And once I solved in the end, if I find S, I know that's solar. If I find W, I know that's wind. So I think that's a lot easier, just using letters that match what you're looking for. All right, now that I have two variables, I'm going to try to set up two equations. First equation, I'll put here. Second equation I'll put here. Let's see, so the first sentence they said, solar and wind generation totaled 1,033. So probably something about 1,033. And don't worry about the trillion. We don't have to put 1,033 and a bunch of zeros. We can just keep in mind that everything in this problem is in trillions. And then just keep that in mind. No need to write all the zeros. So since it says solar and wind energy totaled 1,033, well, we said that S is the number of BTUs for solar, W is the number of BTUs for wind, so together they totaled 1,033. I think that makes sense because we generated S, number of BTUs of solar, W, number of BTUs of wind. That should total, when you put them together, I guess when you add them together, you should get 1,033. So that's the first equation. I think the second sentence that they told us will give us another equation. Okay, they said, wind generated 52 trillion more than 8 times that generated by solar. Holy moly. I think this is one of those ones where you want to maybe read a couple words, write something down, read a couple more words, write something down. So in the very beginning they say wind generated bleh. So what did we call the amount that wind generated? We called it W. So the amount that wind generated, W, okay, was what? 52 trillion more. Okay, so if you have 52 more of something, I think you're adding 52 to something. Does that make sense? Yeah, if I have 52 more dollars than you, that's how many dollars you have plus 52. Okay, so 52 more than what? After that it says, then 8 times, I'm just going to stop there. 8 times something, you're multiplying that by what? That generated by solar. Okay, what did we call the amount that solar generated? We call that S. It should be 8S. So I think what it would be is the amount that wind generated, W, is, in other words, equals 52 more. That means 52 is being added to something. 52 more than 8 times solar. I think that makes sense. And that's our system of equations. That's 2 equations, each of which has 2 variables in it. So that looks good. That was the hardest part of setting it up. And then from there you decide, do you want to use the substitution method or elimination? If you kind of thought one of them made more sense to you than the other, you might want to jump on that one. But to me, I look at this system and I say, you know what? Look at the bottom equation. It already has W isolated. And that's exactly what you want for substitution. So I think I might choose substitution just because it's already in the right form, you know? Okay, so let me rewrite the top equation. The top equation was S plus W is 1033. But since we know that W is equal to 8S plus 52, I'm going to replace that for W here using the substitution method. I'm going to rewrite that guy. It was S plus, but where W was, I'm going to put all that 8S plus 52. Let's see, so W was equal to 8S plus 52. The only bad thing about S is S looks like a 5, huh? So be careful. Oh, what the heck? Why did I put a 52 on the other side? I'm supposed to just be copying exactly what I saw above, 1033. Sorry about that. Okay, and I look at this and I mean I put it in parentheses just to be safe, but there's not really a reason for this 8S plus 52 to be in parentheses. I'm just going to remove them. And now I see that I have 2 like terms here. S and 8S make 9S. And then we have the 52 equals 1033. Now I'm going to start solving for S, and I'll get closer to having the answer. Subtract 52. Let's see, what will that give me? 9S equals, I'll have to do some borrowing here. Let's see. 981, I think. Alright, then I almost have S if I just divide both sides by 9, then I'll have it. Let's see, a 9 goes into 981, let's try that. 9 can go into 981, well 9 goes into 9 once. 9 goes into 8 no times. But it goes into 81 9 times. Okay, so S must be 109. 109, I guess that's BTUs of solar. Okay, so we got S. And then what about the other guy, W? Well, remember in substitution method we said, if you want to find the other variable, the best equation to substitute into is the one that had the variable all by itself. So the blue equation that I wrote over there, W equals 8S plus 52. That's going to be the easiest one to substitute into. So 8 times S, but I know that S is 109 now. I'm going to go ahead and replace that guy. 109. Let's see, and what's 8 times 109? 872 plus 52. So what's 872 plus 52? That's 924. So wind generated 924 BTUs of solar. Or sorry, of wind, sorry. Okay. So that looks good. And remember though, because sometimes a lot of instructors that you'll have later on in your math career, they might be real sticklers about writing, if you have a word problem, writing your answer in a complete sentence. So I might write this as a complete sentence, if I have any room, huh? It says, how about in 2010, what did we find first? Solar generated, we found 109 BTUs. And wind generated, let me erase a little bit here. So wind generated, how many did we say? 924 BTUs. There we go. Okay, that's probably a nicer way to write your answer in the word problems. If they give you words, they want words back. Okay, it looks good. All right, so for sure the hardest part in these problems, like we said, is just setting it up. That's the tricky part. But the more of these you try, the better you'll get at them. Let's look at the next one here. Okay, this one's, I'm just going to read it like we said and just make sure it all makes sense before I try to set up equations. So it says, each course at Pease Country Community College, I think that's not even a real thing, is worth either 3 or 4 credits. The members of the women's golf team are taking a total of 27 courses that are worth a total of 89 credits. That's a lot, huh? How many 3-credit courses and how many 4-credit courses are being taken? Okay, I think all that makes sense in my mind, I think. So I don't have to read it again. Not yet anyway. But I'm trying to figure out what should I let my variables be. Well, what they asked for is how many 3-credit courses. So something is equal to the number of 3-credit courses. And then they also want how many 4-credit courses. Okay, so it's the number of 4-credit courses. And I mean, this one, I don't know if there are actual letters that I would pick to represent this other than X and Y. I guess you could do T for 3-credit courses and then F for 4. I don't know. I think I'll just use X and Y. There's not really a clear letter to use for either of them. Okay, I'll just use X and Y. Okay, now that we've assigned our variables, let's see if we can come up with 2 equations here. First equation. So what do they say? Let me read this again. Each course at blah, 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 it's worth either 3 or 4 credits. Okay, I don't think that's really helping me come up with an equation. That was probably just more letting you realize that there are no 2-credit courses. There's only 3-credit and 4-credit. All right, when the next sentence says, the members of the women's golf team, they're taking a total of 27 courses. You know, I think the 27 courses might give us an equation. Especially when they say the word total, you know it's going to be something equals that number. You know, that's a total. So 27 is the total number of courses. But you know what? We said X is the number of 3-credit courses and Y is the number of 4-credit courses. They said those are the only types of courses. So when you put together all the 3-credit courses and you add it with all the 4-credit courses, that should be all your courses, 27 of them. So I think that does give us the first equation. But even within that same sentence that they mentioned the 27 courses in, then they say that they're worth a total of 89 credits. I think that will give us the second equation. Because the first equation kind of talked about, is more talking about the number of courses. You know, X was the number of 3-credit courses, Y is the number of 4-credit courses, 27 is the number of courses total. But the second equation will talk more about the credits. Number of credits. And they said that there were a total of 89 credits. So I can tell it's going to be something equals 89. But it's not going to be X plus Y equals 89 because, remember, 89 is the number of credits. X and Y is a number of courses. So I got to think about, how about, if you take a 3-credit course, how many credits is that worth? I know that sounds silly. But notice that every 3-credit course is worth 3 credits, right? So if you take X of them, the number of credits you're taking is 3 times X. Because let's say there's 5 3-credit courses. Yeah, for example, just to kind of brainstorm, just to make sure this makes sense. 5 3-credit courses. Let's say that's what you're doing this semester. How many credits is that? Well, you multiply them, right? 5, the number of courses I'm taking, times 3. So that's what we did here, 3x. It's just x is, I don't know the number of courses, that's the only thing. Here I made up a specific example where there were 5 courses. But since we don't know the number of courses, I'll just say Well, however many courses they have, there are 3 times either of those. And then a similar thing for Y. If you're taking Y, that's the number of 4 credit courses, and you want to know how many credits is that worth. Well, each of them is worth 4 credits times however many classes you're taking, Y. There's our system. X plus Y equals 27. 3x plus 4y is 89. And looking at this one, if I'm wanting to decide, do I want to use substitution or elimination, I think I'm going to be fine either way, because if you're kind of more partial to substitution, the top equation, it wouldn't be so hard to get x or y by itself. But if you're partial to elimination, both of these equations are already in the right form. You know, they have x's above each other, the y's above each other, the equal signs, the constants. But for me, I kind of like elimination better. So I'm going to choose elimination method, but you could do substitution and you should get the same answer. All right. So let me rewrite these guys real quick here. So we had the top equation, x plus y equals 27. The bottom equation was 3x plus 4y equals 89. And I wanted to decide which variable do I want to eliminate. Looking at the coefficients of x, I have 1 and 3. Looking at the coefficients of y, I have 1 and 4. The x coefficients are a little smaller, 1 and 3. So I think I will eliminate x. And I think about, okay, what's the least common multiple of their coefficients of 1 and 3? So imagine, what if I had 2 fractions whose denominators were 1 and 3? The common denominator would be 3, right? So that would be my least common multiple. And I noticed the second equation is already perfect. It already has a 3 there. So I think I don't really need to do anything to the second equation because it already has the least common multiple as its coefficient. I just need to multiply the top one by something. So I just look at that x and I say, x times what is 3x? Well, I guess I just have to multiply it by 3, right? Because that would give me 3x. Although I have to be careful because remember, you not only want those numbers to be the same, like I have 3x and 3x, but you want one of them to be a negative. But I can do that easily by just throwing a negative in front of the 3. That'll make it negative 3x. And that way I won't have to do anything to the second equation. So let me see. I'm going to see what happens to that guy up here. Distribute that negative 3. So it's negative 3 times x. That's negative 3x. Negative 3 times y would be negative 3y. Negative 3 times 27 would be negative 81. Okay, that looks good. And then we already decided that the second equation, there's no need to do anything to it. It doesn't need to be multiplied by anything because the coefficient of x is already exactly what we want. So I'll just rewrite it. Let me see. If I add these equations together, the x's are eliminated, which is what was supposed to happen. And when I combine the y's, negative 3y and 4y is just 1y. Or you can just write y. Negative 81 and 89 makes 8. So we have y equals 8. There you go. And this is where I got to look back and say, what did y represent again? Well, it's a good thing I wrote it here in this box. Y is the number of 4 credit courses. So they took 8 4-credit courses. I'll probably have to write this as a sentence later, but it's good to keep that in mind. So now I know y is 8. Now I can substitute that into either of the original equations I wrote here. I think the top one looks nicer, right? X plus y equals 27. I'm going to replace that guy for y. All right, let's see. So if y is 8, let me put that there. Then I can solve for x. It won't be so bad. I'll just have to subtract the 8 from both sides. And then x will be by itself. X will be equal to, that's 19. And if I remember what x was equal to, I wrote it at the top left of this problem. X is the number of 3-credit courses. So there must have been 19 3-credit courses. All right, I should write this as a complete sentence somewhere. Let me see. Maybe I'll say it's kind of up to you. You don't have to write as many words as I do, probably. You could just say, they took blah, blah, blah courses. I'm going to say the women's golf team took, the first number we found was 8 3-credit courses. And you notice I put the word 8, I put it as a word instead of a number because, oh, that was 4-credit courses. Oops, sorry. 4-credit courses. I put it as the word, not the number, because I noticed up here when I wrote 8 4-credit courses, that looked very confusing because it looked like 84 or something. So it's kind of not a bad idea if you see two numbers next to each other that aren't really supposed to be part of the same number. Write one of them as a word and the other one as a letter. Or sorry, one is a word and one is a number. I took 8 4-credit courses, and how many? 19. Oh, I just said I was going to put that as a word, right? Hello. 19 3-credit courses. I like that. Okay. Sounds good. Beautiful. All right. And I guess I should make sure. Is that actually how many courses there were total? That might be a good check. How many did they say? There were 27 courses total. Do those two total 27? There were 8 of them here and 19 of them here. If you add those guys together, oh, that is 27. Okay, good. That's a good sign. Okay, sounds good. Hopefully, I know word problems or applications are always confusing, but the more of them you try, the better you'll get. It's just really the hard part is setting up the equations, I think. It's solving them, as long as the last section made sense, solving them's probably okay. Not great, but okay. All right, let's try the next one here. So example 3, it says, Quick Copy charged 49 cents per page for color copies and 9 cents per page for black and white copies. That's a big difference. If Shirley's bill for 90 copies was $12.90, how many copies of each were made? Okay, all that makes sense, I think. So let me call, what are they asking for here? They wanted to know how many copies of each type were made. And I guess the types they're talking about are color copies is one type, and then black and white copies is another type. So maybe I'll call something the number of color copies. Think about what variable to use, X and Y or something else. And the other one we want to be the number of black and white copies. Copies. Okay. I guess in this one, I wouldn't mind using letters like, say, C for color copies, B for black and white. That might not be bad. Or if you're partial to X and Y, don't think you have to always use letters that stand for things in the problem. You can just use X and Y every time. Like we said before, the only downside is you have to remember what X and Y stood for. Whereas me, when I find C, I'll remember that means color, and if I find B, I'll remember that means black and white. But it's totally up to you, whatever you want to do. So okay, they said, so they charged 49 cents per page for color copies. Okay, I'm not sure what to do with that yet. 9 cents per page for black and white copies. All right, I think that'll have something to do with the cost. Shirley's bill for 90 copies was $12.90. How many copies did she make? Okay. Looking at all the information they gave us, I noticed that they give us kind of price information. They say, oh, color copies cost this much, black and white cost that much, and she spent a total of $12.90. So I think we'll have one equation for price and then another equation for number of copies that were made. I think that's kind of how the information will be broken down. And the easier one, I think, is the second one, the number of copies, because all she made was some number of color copies, that was what we called C, and then plus she made some number of black and white copies, we called that B, and it says she made a total of 90 copies. So I guess if you put the number of color copies together with the black and white copies, you should get 90 total. So I think that one's pretty simple. The price one's maybe going to be confusing, but I'm going to keep in mind that they said the total price that she paid, so total, something's equal to $12.90. I'm going to keep that in mind. But let's see, how would you, like if you made some number of color copies, some number of black and white copies, how would you figure out how much you're paying? Well, keep in mind, okay, it's 49 cents per color copy, which we called C, and then 9 cents per black and white copy, B. So if C is the number of color copies you made, to figure out how much you're paying, you multiply 49 cents times the number of copies you made. But I have to make sure, I'm not going to put 49 cents, I'm going to put $0.49, because the number that's on the right side here, $12.90, that's in dollars. So I better not put just 49 cents. So you want everything in one equation to be of the same denomination, Don't put part of it in cents, part of it in dollars. Make sure you have everything in dollars. So 0.49C, that'd be how much you paid for the color copies. Because C is the number of color copies you made. However many color copies you made times 49 cents is how much you're going to pay for them. And then similarly for black and white copies, you made a total of B black and white copies, however many that is, times 9 cents. But I want to write that in dollar form. 9 cents is $0.09. Kind of feel like that looks squished, huh? Let me write that a little nicer. Oops. Plus 0.09B. I think that works. So 0.49C, that's how much she paid for the color copies. 0.09B is how much she paid for the black and white. That's total. That's how many copies she made. Total price was $12.90. Whew. That was tricky. But there's our system of equations right there. I'm looking at that and I think, okay, I don't like the decimals, first of all, but I remember that I can multiply that top equation by 10 or 100 or 1,000, whatever. Maybe I'll even do that before I decide what method I want to use, because that might affect my decision. Well, that one, since there are 2 digits beyond the decimal, I'm going to multiply the whole thing by 100 there, that top equation, and then rewrite it below maybe. Let me see, what would that guy become? Well, 100 times 0.49C, that would be 49C, because you're moving the decimal to the right twice. And then 100 times 0.09B, if I move the decimal to the right twice, it just becomes a 9B. And then 100 times 12.90, that would move his decimal twice to the right. It would become 1290, like 1,290. And the bottom equation, I don't really want to do anything with it yet because it doesn't have decimals or fractions. I don't want to get rid of anything. All right. Looking at this one, I think a substitution or elimination would be good, huh? Because the bottom equation has C and B. It'd be easy to get C or B by itself in that one. That wouldn't be too bad. But I think I'm kind of partial to elimination because both equations are already in standard form. They both have B above each other. They both have C above each other. The equal sign, the number. So I think I'll use elimination, but it won't really matter, whichever one speaks to you. All right, since we've done elimination quite a few times, I think we can go a little quickly this time. So I want to decide who do I want to eliminate. Look at the C coefficients and the B coefficients. The C coefficients are larger, well, because of the 49. 49 is larger than 9. I think I'll eliminate B. That's my decision. Now you can just keep that in your mind. Don't feel like you have to write that out. So look at the coefficients of B. You got a 9 and a 1. The least common multiple between 9 and 1 is 9. So I need those both to be a 9, which the top one is already there, so that there's no need to do anything to the top one. But the bottom one is not a 9. I'm going to multiply it by 9. But as a matter of fact, I'm going to multiply it by -9. Because remember, they can't just be the same number. They have to be the same number but with opposite signs. So since the top one's already a +9, I'm going to make the bottom one a -9. Okay, the top one I'm not going to do anything to. I'm just going to rewrite it as is, maybe up here a little higher. So what was it? It was 49C plus 9B is 1290. And the bottom equation, now I'm multiplying everything by -9. It'll become -9C minus 9B equals -810. Now we're ready to add those together, and I hope something nice will happen here. Well, the 9B's cancel, which is good. What are we left with here? 49C minus 9C is 40C. What's 1290 minus 810? I might have to think about that. 810. 80. 480. Okay, 480. All right, now I'm ready to solve for C. If I divide both sides by 40. Okay, then what's C there? That's 12. All right. Remember C stood for the number of color copies, so she made 12 color copies. But we also want to know how many black and white copies she made as well. So how would I know that? Let's substitute C equals 12 into, I guess, either of these original equations here, which I don't know. I guess the second one, huh? The second one's nice. I'm going to take that guy. C plus B is 90. And since I know C, I'm going to go ahead and replace that guy. C is here. C was 12. And now I can solve for B by subtracting 12 from both sides. And then I'll know how many black and white copies she made. So 90 minus 12, that's 78. Okay, so she must have made 78 black and white copies. White copies. All right, we got both numbers. Oops. Hello. Now I can kind of sum it all up in one sentence. What's her name? Shirley. I was about to call her Sally for some reason. Shirley made 12 color copies and 78 black and white copies. There we go. That's probably more like what they would want. A nice sentence kind of summing it all up there. All right, that was pretty tough actually, huh? I think anytime money's involved where you're paying for something and these little guys cost this much and those guys cost that much, it's kind of tricky. So these next two problems, these ones are kind of getting us closer to chemistry problems. Especially example 5, we're trying to talk about chemistry. If you're trying to mix two solutions that have so much acid or this percent base. So you might have seen those before, and especially if you're majoring in STEM, so you know, science, technology, engineering, math, you're going to see these again if you have to take chemistry. And I know I've heard chemistry instructors, they say, hey, students, when they come into this class, they don't know how to do these mixture problems. You're not teaching math very well. So I guess it's probably good for you to have seen it, so that way you can say, I have seen this, I just forgot, okay? I'm only human. We all forget things. Hello. So anyway, example 4, though, notice you're talking about pistachios and almonds. Is that what it is? Yeah, pistachios and almonds. So you're probably not going to see pistachios and almonds in chemistry, but it'll give us an idea of how to do the next example, which you will see in chemistry. They're very similar. So okay, we got this company called O Nuts, exclamation point, sells pistachio kernels for $10 per pound, okay, and almonds for $8 per pound. Sounds good. They want to know how much of each type should be used to make a 50-pound mixture that sells for $8.80 per pound. All right, it all makes sort of sense. I can kind of picture what they're doing here, mixing two things, and they want it to cost this much, and they want this many pounds. All right, but what are they asking me for? I'm going to call those the variables. I say how many of each type, or how much of each type. So I guess since there are pistachios and almonds, we'll say the number of pounds of pistachios will be something, some variable, and the other one, the number of pounds of almonds, will be the other variable. Let's say, so I guess I'll do P for pistachios, A for almonds. Or you could do X and Y or something, doesn't matter. But I just like P and A because then when I find one, I'll know what it is. If I find A, I'll know it's almonds. If I find P, I'll know it's pistachios. Okay. So what do they say? You know what happens in a lot of these? You might notice this, but since you're trying to come up with two equations, usually one of them is fairly simple to get, and the other one's a little more complicated. So for example, they're trying to mix a number of pistachios, we call that P. They're trying to combine that with a number of almonds, which we called A, and they want a total of 50 pounds. So I think one equation would just be very simple. The number of pounds of pistachios that I mix plus the number of pounds of almonds I mix, they want it to be 50 pounds total. So that one's really easy. It's the other one that's going to be complicated. It's going to involve the money part. So you know what? For some reason, I always had a hard time with these problems when I took chemistry, and I think it was never explained to me very well, and I never really got it. For some reason, when someone showed me the picture, like they drew a picture, it sounds silly, but they said, okay, check it out. We got some pistachios here. Let's say these are the pistachios, the red, I don't know why. Pistachios. That's like a big bin full of pistachios. We're going to take those, combine them with this bin full of almonds. I don't really know how many pounds of each there are, but it's just some amount. And I'm going to get some mixture, I guess. I don't know what. Yeah, I guess I'll just call it a mixture. Mixture of the two. So let me label the price. Okay, pistachios, they said, cost $10 per pound. And then almonds were how much? $8 per pound. And the mixture they want to be $8.80 per pound. Okay, that kind of gathers all your thoughts and connects the dollar amount with what kind of nut it is and all that. But the way you want to set up your equation is, I guess you want to say, once I mix these two, how much will the pistachio portion cost? Well, pistachios are $10 per pound, and you have P pounds of pistachios. So the cost of this will be, let's see, 10 times P, because P is the number of pounds. And then A is the number of pounds of almonds. So how much will this cost? Well, it's $8 per pound for the almonds, and I'm combining whatever A is, A number of pounds. And then how about for the mix? So the mix was 50 pounds, right? There were 50 pounds of the mix. How much did it cost, or how much would it cost for this mixture? Well, they said it costs $8.80 per pound, and I have 50 pounds. So that one's a little different because the mixture, I know exactly how many pounds, 50. Whereas with the almonds, I didn't know how many pounds, I just call it A. And then the number of pounds of pistachios, I called P. So that'll give us our second equation. It's 10P plus 8A equals, okay, what's 880 times 50? Let me see, I'm going to go way down here. 880 times 50, 44, okay. How many digits beyond the decimal? 2. Okay, so $44. Wow. Really? That's a nice number. Okay, sure, why not? Don't question a good thing. So there's our other equation. Oh my gosh. For some reason, the picture makes it make sense to me, especially when I label the cost of each thing and how many pounds, you know? Like up at the top, I put how many pounds, this many pounds, this many pounds. Oh well. If that kind of complicates it to you, sorry. Some people, these just make sense, but for me, not so much. I had to really put a lot of thought into these. Now we have our system of equations. All right. And this one, both equations are of the same form. You got the P terms above each other, the A terms above each other, all that. I think I'll use elimination. And looking at the system, I noticed that the coefficients of A are slightly smaller than the coefficients of P. So I think I might go for A. And you notice, if I want to get them to be the same number, kind of like in the last one, I'm just going to multiply the top equation by -8. Because then the coefficients of A are both 8, except one's negative and one's positive. So I think that'll be perfect. All right, we're getting the hang of this, I think. Let me rewrite the top one, distributing the -8. -8 times P, got that. -8 times A, got that. -8 times 50 is -400. Okay, let me bring down the bottom one. Let's see, yeah, and the second one we don't need to do anything to, it's perfect. Wait, is that right? -400. 2. Yeah, huh, okay. And let me bring down the second one. 10P plus 8A is 44. Oh, you know what I think I realized? Oh my gosh, I multiplied these guys wrong. These guys over here, 880 times 50, that's not 44, that's 440. I'm sorry, you guys. So this should be a 440 right here and here. I'm sorry about that. Hello. Decimals, come on. They're terrible, am I right? Sorry about that. So that should be a 440. All right, sorry about that. Now we're ready to add these guys. The A terms disappear. The -8P and the 10P make 2P. And the A's are gone. What's on the other side? -400 and 440 makes 40. We almost have the value of P. Let me divide both sides by 2. So it looks like P is 20. And remember, P is the number of pounds of pistachios. So there must be 20 pounds of pistachios. All right, so we got that. How about almonds, though? How would I find that out? Well, I'll substitute P equals 20 into one of the original equations. The green one was the nicest one, right? The P plus A is 50. I like that one. And now that I know P is 20, I'm just going to replace that guy and see what A is. 20 goes where P was. Move the 20 over. So A must be 30. Huh, all right, sure. Why not? And remember, A was the number of pounds of almonds. Oops, why do I keep doing that? Sorry. All right, I think we can kind of sum this up by writing it in a sentence. I kind of like the name of the company. It's way too funny. Oh, nuts! Exclamation point. Should mix 20 pounds of pistachios and 30 pounds of almonds. Nice. We did it. Yay. Look at that. We helped out a company in need. Isn't that so thoughtful of us? Oops. Jeez. All right. Only one more. And this one I think is very similar to this last one. I mean, it's not as interesting because it's not about food. I always like food. But it's still a similar thing. So this last example, okay, they say eChem testing. These people have a solution that is 80% base and another one that is 30% base. Okay, so I guess the 80% and the 30%, think of that as similar to the cost of the almonds and pistachios in the last one. So I kind of like to write these guys out. So one, we have an 80% base. I'm thinking of this as a bin full of some solution, I guess. So we got 80% base. Okay, and I think they're wanting us to mix that with something. The other one was 30%. Okay, sounds good. 30% base. And then we want to mix it and get some other solution. They say how much percent? Oh yeah, 62%. Some kind of solution that's 62% base. Sure. All right, so I got my picture ready. Then they said, and they want the solution that's the mixture to be 150 liters. All right, so they want 150 liters of the mixture in the end. The 150 liter solution will be prepared by mixing the two solutions on hand. Okay, yeah, the 80% and the 30%. How much of each should be used? All right, that gives away what we should call things. And I don't know if you want to call, like, if I say something is the number of liters of the 80% base solution, and the other one is the number of liters of the 30% base solution. I don't know, since those are just kind of numbers, I don't know if I would call them like E for 80 or T for 30. I'm just going to call those guys X and Y, since there's not really, to me, there's not really a clear letter to use other than X and Y. All right, so it looks like they want us to take X liters of the first 80% base, combine it with Y liters of the second base, and get 150 liters total. So, but we want two equations, and like we said in the last one, there's always one equation that's really easy, because you're going to take some number of liters of the 80% plus some number of liters of the 30%. They want you to combine it to get 150 liters of the mixture. So I guess the equation that just talks about number of liters, that one's pretty easy. Number of liters plus number of liters, they want them to add up to 150. But the other equation will be more complicated. It'll have to do with the percents more. Like what percent base is each one. So I have to do that over here in this brainstorming area with my pictures. For some reason the pictures make it make sense more. I don't know why. It's crazy. But so how about for the 80% mixture? I guess if I want to know, okay, this first solution, the one in the blue bin, it's 80% base. If there are X liters of it, how much of those X liters is base? Well, I guess you would say it's 80% times X. But I guess, yeah, that sounds good. 80% times X. That's how much base there would be. 80% of however many liters. That's, I guess, what you're trying to figure out here. How much base is in each one? Plus, how much base is in the second one? Well, it's 30%, but times there are Y liters of that guy. And then the mixture part, you want the percent to be 62%, but there are 150 liters of that guy. That's how much base. Much base. Yeah, 62% of 150, whatever that is. And I think that looks good. Hopefully I can multiply these numbers right this time. What's 150 times 62? Be careful here, careful. 9,300, wow. All right, so it looks like 80x plus 30y equals 9,300. There's our second equation. All right, we're doing good here. Plus 30y. All right, we got a system. But now that I look at the system, you know, the complicated equation we just found has some big numbers. The second equation, though, the simple one, it doesn't really have big numbers. It's kind of nice. And I notice these are in the same form. You have the x's above each other, the y's above each other, the equal signs, the numbers. So, I mean, I know I'm kind of partial to elimination, but I'm going to use elimination. And I'm looking at x's and y's. And notice the y coefficients are smaller. So I might try to eliminate y. And I notice between 30 and 1, those are the coefficients of y. The common denominator, or the least common multiple, would be 30. Since the top one's already 30, I need to make the bottom one 30, but you want them to be opposite signs, so I'm going to go ahead and multiply the bottom one by not just 30, but negative 30. And I think that should do it. So I'm keeping the top one the same because that one had exactly the coefficient of y I wanted. I'm not going to change that guy. He looks okay. But the bottom one, everything's multiplying by negative 30. So I'll have negative 30x minus 30y is, what would that be? Negative 4,500? Let me see, I have to make sure. I'm paranoid about multiplying wrong now. Okay, yeah. 4,500. Alright, now these guys are ready to be added together. The y's will disappear and we'll know what x is. We got 80x and subtract 30x, that's 50x. The y's disappear. 9,300 minus 4,500 would be 4,800. Is that true? Yeah, that's true. Okay. And we can solve for x all the way by dividing both sides by 50. Alright, then we'll have x all by himself. I'm going to have to divide that over off to the side. 50 into 4800. 50 cannot go into 48, but it can go into 489 times with 30 left over. If I bring down a 0, 50 goes into 306 times. Alright, so 96, that must be x. And above, I think we let x equal, what was it? Oops. X was the number of liters of 80% base solution. Okay, good. So we got 96 liters of the 80% base solution. Alright, but they also want to know how many liters of the other guy. I'm going to go back and look. What was the simpler equation that I'd like to substitute into? Oh, for sure, this guy. X plus y equals 150. Come on. I don't think it gets much simpler than that. X plus y is 150, and replace x with the value I just found, 96. Let's see here. Oops. Hello. So 96 here. And if I want to solve this for y, all I have to do is subtract 96 over and I'll be ready. 96. Alright, so y would be, what would that be? 54 liters of, and that was the 30% base solution. Base solution. And you know how it goes. We should probably sum it all up. After all that work, I'm kind of not too excited about writing it all out, but that's okay. So I'll say this laboratory or this lab should mix 96 liters. You're free to abbreviate. Don't feel like you have to write the word liter out. Liters of the 80% base solution with how many liters of the other guy? 54 liters of the 30% base solution. Alright, sounds good. So yeah, keep in mind that you'll see those again if you take chemistry. But if you don't take chemistry, then you won't see those again, but you know, your mathematical understanding will be a lot better. You know, you'll have a good mathematical foundation and all that good stuff. Okay. So thanks for listening, and I hope you have a good day. Take it easy. Enjoy yourself. I'll see you in the next video. Thanks.